Okay, guys, so we're going to start talking about enthalpy. The symbol for enthalpy is a H. And so the standard enthalpy change, your symbols for that are going to be, it's a change, so there's a delta H, and the word standard has meaning as well. It's not just it's just a standard procedure. It has meaning. So, and that standard is this little naught symbol right there, superscripted to the right of the H. And so, what does that standard mean? That means standard conditions. That's so frustrating. And what are standard conditions? Well, that is 101 kPa and not 0, but 25 degrees Celsius. And so I need you to make sure that you understand that there's a difference between standard conditions and standard temperature and pressure. STP is 101 kPa and 0 degrees Celsius. Standard conditions are 101 kPa and 25 degrees Celsius. They are not the same. Now, let's tie this to what we've been talking about. I did a little bit of this in the last video, kind of started to tie these together. So we have determined that Q equals MC delta T. Okay, now enthalpy, just in a basic sense, what is enthalpy? Well, H is equal to the energy content of a substance. That's really way oversimplified, but that's basically what we're going to consider it for the level of this course. And so energy content, if we lose energy, then we are going to lose heat, and we define heat as Q here. And so a delta H, we can effectively say that a change in H would be equal to Q. Now this is not, if you go in and you major in science in college or chemistry, it's not true. However, it's true in some situations. And so we're going to make that, we're going to be in those situations. So we are going to make that substitution that the delta H is equal to MCAT. When is it really true? Well, it's true under constant pressure. That's when it's true. And if you think about our laboratory, we're doing labs in the open air environment, and the air pressure is not changing. And so we're going to make that assumption that we're under constant pressure. If you had a closed cylinder where the pressure is building up or changing, then that would not be true. Okay, we need to talk about exothermic and endothermic. You sure already know what these are. So exothermic, heat is released. Endothermic, heat is absorbed. We need to identify where the heat comes from. We cannot create or destroy energy. It must come from somewhere. And so in a laboratory experiment, most of our experiments are going to be done involving water solutions, aqueous solutions. So we have this aqueous solution. Inside of this aqueous solution, we have chemicals that may react with each other, okay, and form a new substance. And so the chemicals themselves are going to be the thing that is gaining or losing heat. In this case, the water is surrounding it. So we have the system. In this case, this would be our system. And the water, as well as the rest of the room, are the surroundings. And heat flows between the system and the surroundings. Okay, that's where heat flows between these two things. And let's say that our chemical particles are going to release energy. So they will release energy into the surroundings. In this case, the immediate surroundings would be the water surrounding the chemical particles. And so as this reaction proceeds, if we have a thermometer in our solution, the water is absorbing the energy from the system, and the water temperature is going to rise. It's going to go up. So in an exothermic reaction, the surroundings get warmer. Now, if however, this is an endothermic reaction, the system is going to absorb heat from the surroundings. In this case, the immediate surroundings being the liquid solution. Then once again, if we have our thermometer in there, in this case, the water is going to actually get colder. because the chemicals are absorbing heat from the water. And so that would be an endothermic reaction. And so make sure you understand what's happening to the system and surroundings temperature-wise, energy-wise in an exo and endothermic reaction. So what happens to the Q? So Q, or heat, being released, you want to look at it from the perspective of the system. You always look at Q from the system's perspective. So I still have the endothermic drawn up here. What's happening to the Q for the endothermic? Energy is going into it. The Q is getting larger. So Q is positive. Here Q is negative. Now we just said Q is equal to delta H, which for our cases is true. And so this is what you need to know, that for a endothermic and exothermic reactions, you need to know the signs of delta H. Scratch that out there. So delta H is negative for exothermic, delta H is positive for endothermic. Now let's look at that on a diagram. So what you're going to see here is an enthalpy level diagram. You need to know that this is called an enthalpy level diagram. And so on the left, or the y-axis, we're going to have enthalpy, and on the x-axis, we're going to have reactants and products. And I forgot to mention something earlier. I want to go ahead and mention it now. Enthalpy, H, is not measurable. You cannot measure it. We can't measure it. We don't know what H is, what the absolute value of H is, but we can measure the change in H. That is measurable. And so that's just an important little thing to know, is that we can't measure H directly, but we can measure the change in H, the relative change in it. And so I'm not going to put any units over here because I don't know what the units of H are, the actual like numerical values, because we don't measure it. We can measure the change in it. And so let's look at a reaction. Let's say that we did CH4 plus O2. And that would make CO2 plus water. And you should recognize that this is methane, and this is a combustion reaction, so that's also going to produce heat. It's an exothermic reaction. And so what would the enthalpy level diagram for this look like? Well, our reactants are going to have a enthalpy, and our products are going to have an enthalpy, and there's going to be heat released in this reaction. And so the reactants have more enthalpy than the products. What's happening is that the reactants give up energy. They give up heat, and so their net energy content, their net enthalpy level decreases as they release that energy. And so for an enthalpy level diagram, we have this change, and we could actually just do a little dash line here, dash line there, and that is delta H. And that, whatever that change is, that's the delta H. And we can measure delta H. And you can see that it goes down, and so delta H is negative. It's being released as we proceed through this reaction. And so this is what an enthalpy level diagram for an exothermic reaction would look like. You're going to start high, and you're going to go lower in this reaction. Now, it might be there are a couple ways you could do it. You could do the line. Get out another line over here, and it could just be a gradual curve, or it might be straight down. It doesn't really matter how you do that, but whether it's gradual or straight or whatever, that's not really important. All right, what if we had an endothermic process, one that's absorbing energy? Well, in that case, we would start with low reactants, end with high reactants, and the enthalpy is going to increase. As it absorbs, it's getting higher. As it absorbs that energy, we increase our entropy. Okay. Now, the last thing is about relative stabilities. In chemistry, the lower the enthalpy, the more stable the chemicals are. The higher the enthalpy, the less stable the chemicals are. We're talking about like thermodynamic stability here. And so if you're looking at a endothermic reaction like we have here, and I asked you about the relative stabilities of the products versus the reactants, well, you would say that the products are less stable than the reactants because they are of higher entropy. Or you could say the reactants are more stable than the products because they are lower in entropy. And so you need to understand this idea of stability as well, relative stability between the products and the reactants. The higher they are, the less stable. The lower they are, the more stable. And so what this tells you is that an endothermic process is producing less stable products. Doesn't mean it can't happen, because they do. And an exothermic process produces more stable products.